We're here in the workshops of Saint-Quentin-en-Yvelines, where Damien is busy assembling a LEAP engine turbine. He has worked for years here in the assembly department, so he's perfectly familiar with every part of every turbine. He could practically assemble them with his eyes closed. The part that Damien is assembling here are stage 2 nozzles for the LEAP engine. And Damien will tell you how this part was made. What? You don't know? Really? Where does this part come from? It says Gennevilliers. All right then, let's go and see. Here on the Gennevilliers site, many different parts are made for civil and military engines. And it all starts here in the design office, where the team designs parts according to strict specifications. While incorporating thermal and aerodynamic constraints, as well as mechanical requirements, the team precisely models the part. We can see our turbine blade, which for the moment exists in a virtual state. To make it into a real object, the CAD file is sent to the Tools and Product Method office, where they'll work on it to adapt it to production. The office works collaboratively with the Process and Product Method team. The goal is to jointly define how to produce this turbine blade industrially. First, the team models a cluster structure specific to industrialization. Then it develops injection tools, in other words, molds. The production of these molds is outsourced, but of course, they are all systematically checked by the office. So far, so good? Let's move on to production. To obtain these parts with complex shapes that include voids, the team uses a 6,000-year-old method, lost wax casting. You start by producing an object in the shape of the desired cavity, the core. Here we inject a mixture of binder and ceramic into this machine to produce that famous core. This material is still fragile. We therefore need to cook the core in order to harden it. This operation is carried out in baking sand. This enables the core to keep its shape even under heat capable of deforming it. Our core is now much stronger. All the cores are meticulously deburred and checked. Once prepared, they are placed in the famous injection mold. The 4 cores inserted here will form the 4 cavities of our turbine blade. Wax is injected. And what do we discover when they come out? Wait for it. Magnificent! This is our turbine blade, made of wax. It immediately undergoes ultrasound and radiography tests to verify that the core is correctly centered in the wax and that it didn't crack during the injection. The wax model is prepared to form the famous cluster developed by the Method Office. These clusters are taken for cleaning, which is essential to remove all traces of handling or release agent. Because the blades must be perfectly clean so that nothing interferes with the adherence of the material, they will be covered in the ceramic slip. Slip is a kind of liquid paste. The clusters are soaked in it, then sprinkled with ceramic sand. Once dried, the whole forms a crust. This operation is repeated several times until a sufficiently thick ceramic shell is obtained. Now we have to melt the wax that's inside. It's a delicate operation because the clusters are composed of wax parts encased in ceramics. The wax will expand in the heat, but not the ceramics. So to prevent the ceramics from cracking, the operation is carried out under pressure in an autoclave. Then a cooking operation hardens the shell and burns all the wax residue. The ceramic core is maintained inside. Now we need to check the impermeability of the shell in which the metal is going to be cast, with a non-destructive process, of course. So another radiography or ultrasound test? No? Really? With methyl blue solution, of course. The shell is filled with it, and the color will reveal the slightest defects by making them turn blue, like that little bit here, and right there. The compliant shells are then taken to be cast. Not quite yet, actually. So what do we have in here? Some references require preparatory wrapping, because when the metal is cast, upon reaching the edges, it starts to cool down, so to harden, and that can prevent an even distribution in the finest parts. Pre-wrapping ensures that the temperature is controlled for specific parts. So all good to go this time? The shells are ready, so we start to preheat. The metal is loaded and brought to the melting point. The preheated shell is put in position. Casting completed. The cooling stage is crucial. It's the precise control of the cooling process that gives the material its high-performance thermomechanical qualities. A cooling ring is used to control this phase of directed solidification. The metal retracts slightly, which causes the ceramic layer to develop cracks. It almost makes you want to shake it off to completely clear the part. In fact, that's exactly what happens during the shake-off operation. Here, finally the rough blade is revealed, still arranged in clusters. Now we separate them. You will notice that our core is still inside. To get rid of it, we're going to dissolve it in a soda bath. That's the machine just behind. The turbine blades are taken for soaking. And when they come back, how do they look? Perfect. There is still one finishing step left to get this blade spick and span. But in fact, is this part compliant? It undergoes a full range of tests: macro control to inspect the grains, dye penetrant testing to identify visible surface defects, ultrasonic thickness control, dimensional inspection, and internal health control by digital radiography. What about traceability? Time to head over to the machining assembly and coating unit. Metal stellites are added to the parts that will be in friction to reduce wear and tear. A grinding operation called rectification will give the part a clearer and more precise shape. An adjustment will round off sharp edges. These finishes are very precise. This three-dimensional measuring machine performs an impressive 150 measurements per part. According to their position and their function in the engine, some parts will be subjected to very high temperatures. In order to cool these parts, a drilling operation adds holes to accelerate the circulation of air. This micro-drilling is done with water. Using an electrode all the same, calibrated to the diameter of the hole is hollow so that water can pass through. Seeing how fine the rod is, you immediately understand that the drilling action is not mechanical, but electric. Some parts are now going to be covered with several small complementary parts. These complementary parts are attached using a solder bead and then melted in the oven. The furnaces are also dedicated to heat treatments or thermochemical treatments, where the parts are finished off with an external coating. Here, finally, is our finished turbine blade. An airflow test, as well as penetrant and radiography tests, check the quality of the part. But before it goes off for delivery, this machine still performs some operations. Laser marking, adding a manufacturer's number, weighing, and in the final touch, the turbine blade's position in the box is photographed to ensure complete traceability. Now we're all done. The box is ready. All we have to do now is deliver it to Damien, our fitter in Saint-Quentin-en-Yvelines. Keep up the good work, Damien.